Okay, so last time we were talking about conceptually and qualitatively how a MOSFET controls current. We talked about inversion, and so today we're going to continue along that discussion and talk about the different operational modes and some of the IV characteristics and so on. So really quick from last time, we said that the way that a MOSFET controls current is through inversion. We're trying to make an electronic switch where the voltage at the gate controls whether current is allowed to conduct between the source and the drain. So when the transistor is off, the gate region is a p-type semiconductor. This is an example of an NMOS device. The gate region, the channel region is a p-type semiconductor, and the source and the drain are n-type. So if you make a circuit diagram of this, you have two back-to-back diodes, so you can never have current flow between the source and the drain. When the transistor is on, you switch the p-type material to an n-type material. Three n-type materials together is the equivalent of three different resistances, so this allows current between the source and the drain. So the interesting thing about the MOSFET, why it's called a field effect transistor, is because the MOSFET allows you to switch this p-type material to an n-type material just by applying a voltage to the gate. And the way that works is through this structure. Do you think we would close that door over there? A little loud. Thank you. So the structure of a MOSFET looks like this. You have a p-type substrate. This is an NMOS device. Okay, I'm going to go over the NMOS device in class, but I think I can expect you to look over the structure of a PMOS device and understand the PMOS device by analogy. These are the same type of principles apply to the PMOS device. This is what the structure looks like. The source and drain are N+ regions. The substrate is p-type. We talked about this in class last time. There's an insulating material on top of the substrate, and on top of that there's a metal region which acts as the gate. So this is these gray boxes over the source and drain. Those are metals, and this orange material is metal, or it could be made of a material called polysilicon, which acts as a metal. It's a highly doped semiconductor. So the concept was that if we want to switch the material, we can apply, if we want to switch this substrate material from p-type to n-type, we can apply a voltage at the gate. And when you apply a positive voltage at the gate, you build up a bunch of positive charges at the gate. And those positive charges create an electric field. That electric field is pointed away from the positive charge, so it's pointed down. Okay, you're applying a voltage between the gate and the source, but the source is connected to the substrate. Okay, so it's like applying, it's similar to applying a voltage just between the gate and the substrate itself. So think about this as a capacitor. There's positive charge buildup on top of the dielectric. You get a negative charge buildup at the bottom of the dielectric. So how that happens is the electric field, it pushes away the holes in the p-type material. It pulls in the electrons. So a p-type material has a lot of holes and very few electrons. But in this region, we're pushing away all the holes that are there. We're pushing away the majority carrier. We're pulling in the minority carrier, the electrons. So right at the surface, just below the gate, this becomes n-type. Okay, now you have an n-type channel that connects between the source and the drain. Now the device is on. You can have current go between the source and the drain. So by applying this gate voltage, we've effectively switched the channel material from a p-type material to an n-type. And this happens very rapidly. It can happen within less than a nanosecond. Okay, so you have a very, very fast switch. And as we talked about, the switch is a basic building block for microprocessors. That's why this is the most popular type of semiconductor device in sheer numbers. Every computer chip has more than 1 billion transistors on it. So this is where we're going to pick up today, the triode region. Now we're going to talk about what happens when we start applying a VDS to it. So in this example, we were just applying a VGS, and we turned on the channel. In the triode region, we also apply a VDS. We apply a small VDS. And that VDS is less than VGS minus the threshold voltage. So we'll talk more about this a little bit later. Okay, but just for right now, assume that we're applying qualitatively a small drain to source voltage. So the question is, why does the channel become thinner near the drain? If we compare the channel when it's when we don't apply a VDS, it looks, the electron density is equal all the way through the channel. But when we apply a voltage to the drain, the electron density becomes less on the right side of the channel compared to the left side of the channel. This is showing sort of a triangular shape, but actually what I'm trying to show here is that the electron density is lower here and higher on this side. Where do you think that sort of non-uniformity arises from? This is kind of a tricky question, but if you have any guesses, you can try.
You're reducing the field at that corner where you're applying the additional bias right to the diode.
Absolutely, you end up reducing the field. Yeah, very good, very good. So when you apply a bias to the right side of the you're applying a voltage to the right side of the material, and a current flows through here. Okay. What happens when we apply a voltage across a resistor? Let's look inside of a resistor. Okay. So we're applying 10 volts across this resistor. Now, with the multimeter that you have in the lab, you can only measure the voltage on this side of the resistor and this side of the resistor. You don't have the ability to measure the voltage inside the resistor along its length. But if you did, what you would find is that the voltage varies linearly across the resistor. If you put a 10 volt across a resistor like this, you'd have 10 volts on one side, 0 volts on the other side. But if you could measure, say, halfway in the middle of the resistor, you'd find that the voltage there was 5 volts, right in the middle between the two. Okay, so the voltage drop inside in a resistor, it drops linearly with position. Okay, that's the first important concept. Now, in a MOSFET, this also happens. We're applying a voltage on the drain. We're applying a VDS, so voltage between the drain and the source. Now, this channel here, the inversion channel acts as a resistor. Oops. Okay. It acts as a resistor, so there's a higher voltage in the channel on this side, and there's a lower voltage in the channel on this side. All right. That voltage difference in the channel is partly responsible for why this type of non-uniformity arises. It has to do with the fields. Let's go over this slide first. This slide is just showing that if we were to plot the channel voltage, VC or VCH, the voltage right across this line right here, we'd see that the source, the source is at 0 volts, so the voltage here is 0. As we go from left to right, the voltage increases and it goes up to whatever the drain voltage is, VD. It increases linearly along there. So, let me show another concept here. Bringing in the concept of a capacitor. We've seen this many times before, so I'm just drawing it again so we all have a basis here. You put a voltage across two parallel plates, and there's a dielectric material in the middle there, and the charge is equal to CV. Okay, the charge is the number of positive charges and the number of negative charges here. So Q is equal to the capacitance times the voltage applied. Now this voltage is V plus minus V minus. Right, the voltage here is V plus, and the voltage here is V minus. So in other words, the charge is proportional to the voltage difference across the two plates. All right, that's something that you know pretty well by now. So, but looking at this problem, in a MOSFET, So you have the dielectric material here, and this is the source, this is the drain, and then this is the gate. Now, whatever voltage you apply on the gate is connected to a metal here. So whatever voltage you apply here, that voltage is the same everywhere here. So we're going to call this V plus. The value of V plus is the same everywhere in the gate. V minus is the V minus in the channel here. So this is the channel voltage. All right, and as we saw in the graph, the channel voltage increases as we go from the source to the drain. So this is the channel voltage, or V minus. So what will happen is that V minus is larger on the right side than it is on the left side. So what do we expect the charge to be on the right side of the transistor compared to the left side? What is the Q going to be? Q is equal to C times V plus minus V minus. So which side is going to have more charge? The source side or the drain side? So the V plus is constant for all parts of the channel. V minus is increasing as we go from left to right. So the source side is going to have the most charge. So the Q, we call this Q max. The maximum amount of charge is on this side. The minimum amount of charge is on this side. So if I were to say this another way, if we were to plot Q, oops, what's going on here? Yeah, I ran out of ink. Microsoft. Okay. I really like this tablet though, it's pretty cool. So if we were to plot Q in the channel, we'd find that the maximum Q is on this side, and the Q drops, the amount of charge drops as we go to the right side, because the channel voltage is increasing from left to right. And again, Q is equal to C V plus minus V minus. All right, so we have more charge on the left side of the channel, less charge on the right side of the channel. So going back to this diagram, that's why it's schematically shown this way. You actually have less charge buildup on the right side of the channel compared to the amount of charge buildup on the left side. Now this charge is important, right? Without this negative charge in the channel, you don't have an N-type semiconductor. So if the amount of charge on the right side becomes very less, if it becomes small enough, then what's going to happen is that the channel will ultimately pinch off. This pinch-off effect occurs where the gate to channel voltage, the V plus minus V minus, it becomes less than the threshold voltage. The threshold voltage is the minimum voltage required to turn on the device. So we haven't talked about that yet. That's going to come later. We're going to calculate the threshold voltage. But conceptually from this thing, you can see that that the right side of the channel has less charge than the left side, and if you increase the drain voltage large enough, you're going to actually get a situation where you start to pinch off the channel on the right side. This is what leads to the saturation effect of the transistor. So you remember on the first yesterday's class we talked about the triode region. In the triode region, the MOSFET behaves, you have this linear IV characteristic, so it behaves very much like a resistor. Between the source and the drain, it looks like a resistor. That's why you have the straight line here. The saturation region or it's flat, this is where the pinch-off effect happens, and the pinch-off effect prevents the current from increasing any further beyond a certain saturation value. It's like you're taking a hose. The analogy is, if you take a hose and you pinch it off on one end of it, that's going to prevent the amount of water that's going through the hose, right? It's going to limit it. And that's essentially what's happening here with the MOSFET. This channel gets pinched off because of this effect. So this causes the MOSFET to enter a different region of operation, which we just resulting in that different IV characteristic. So the pinch-off region occurs if the drain to source voltage exceeds VGS minus VT, threshold voltage we'll talk about. So if we're deriving the IV characteristics, we're going to derive the current voltage characteristics first. This is something that these relationships you've seen in Electronics 1, the triode equations and the saturation equations, we're going to derive those first. Then we're going to get into calculating threshold voltages. So to begin the process of deriving the transistor current, so we have to look at some basic relationships related to conduction. Okay? Because we're going to treat this region as a resistor. Okay? The resistor has some sort of conductivity associated with it. We found that the resistance is equal to R. The resistance R is equal to L divided by sigma A, right, from chapter 3. We figured out how to calculate the resistance of a semiconductor. So we're bringing back some of those concepts right now. The conductivity is equal to, the conductivity sigma is equal to the mobility times the volume charge density, coulombs per centimeter cubed. In an N-type semiconductor, this is equal to small q, 1.6 times 10 to the negative 19 times N. N is the number of electrons per centimeter cubed. So this large Q is equal to Q times N in the case of an N-type semiconductor. It's equal to Q times P in the case of a P-type semiconductor. So these are all relationships that we saw earlier. We're also bringing back something you learned also from the earlier chapters. V equals IR. Okay, and in this case, another version of this formula is I is equal to V times the conductance, and the conductance is equal to mu times the volumetric charge density. Okay, so now we're going to derive the IV characteristic of a MOSFET, and we're going to do it mathematically. So there's going to be some integrals involved, but we're going to go from first principles. So first, recall that there's a mobile charge in the inversion channel due to minority electrons. We're basically talking about these minority electrons here in the channel. The charge density depends on the location, so the channel conductivity changes as well. So tell me, which side of the channel is going to have a higher conductivity, which is going to have a lower conductivity? We know that this side of the channel has a lower charge density, and this side has a higher charge density. So which side of the channel is going to have lower conductivity? The right side of it. Okay. Whichever side has more charge is more conductive. Whichever side has less charge is less conductive. All right. So this is why we actually need to use an integral to derive the current. Sorry, jump here. Now, why do we need to use an integral to derive the current? Let's go back to a very simple example here. Suppose we just have an N-type semiconductor. This is the type of thing that you did in the lab. So let's say you have just an N-type semiconductor in the top view, and you have two pads connected to it. So this is metal, and this is an N-type semiconductor. This is the top view. In your lab assignment, and from the earlier chapters, when you're trying to find the resistance of this thing, remember this thing behaves as a resistor. So the resistance is equal to L divided by sigma A. All right. And so this is a very simple calculation to do. And remember, the sigma is equal to Q times mu n times n for an n-type semiconductor. Very simple calculation. What we're trying to do right now is we're trying to find the resistance of the channel. We're trying to find the resistance of the channel in the case of the MOSFET. We cannot use this simple formula, and the reason why we can't is because we have a situation where this part of the channel, this sigma here, is different than the sigma on the right side of the channel. The sigma is changing as we go through the length of the channel. So you can't just use a simple formula to do it. You actually have to use an integral. And the way that integration works, if you remember back to your mathematics classes, the conceptual principle behind it is, let's say we have, and I'm applying those concepts to a resistor type problem here. Let's say we have a resistor here, and let's say this is X, and the conductivity is like this. Let's say the conductivity goes down as a function of X. Okay, we know one way we can solve for this problem, or one way we can figure out the resistance, is by splitting this up into smaller resistances. So we are going to take, so this is your resistor. This is the N-type semiconductor. We are going to break it up into smaller pieces. Okay? In other words, we're going to break up that resistor into a series of smaller resistors. And we're going to find the resistance of each one. So this will be R1, R2. Okay, and each one of these resistances is going to be different, all the way up to Rn. So as we talked about, when we're talking about the MOSFET, the conductivity is less on the right side than it is on the left side. So Rn is obviously going to be greater than Rn minus 1. The ones on the, as we go from left to right, the resistance are going to be increasing. Okay, so we'll get to that in a second. Now, the way that we find the total resistance is by breaking it up into smaller pieces and saying the total resistance is equal to R1 plus R2 plus R3. Now, from mathematics, like if you take a function and you break that function up into smaller pieces and then you add up those individual pieces, that concept is what integration is all about. The Riemann sum, if you guys sort of remember this concept of a Riemann sum from calculus, when you take the value of a function and you consider each one of the individual values and you cumulatively summing up those values, which is basically what we're doing here, that means you have to do integration. So let's go back to this and mathematically work it out. So the conductivity at each one of these parts in the channel is going to be determined by the charge, the amount of charge that we have there. Now, we figured out earlier that the amount of charge varies as a function of x. So the amount of charge is equal to C times V plus minus V minus. So this is the gate voltage minus the channel voltage. And I didn't mention this earlier, but we also have a threshold voltage term in here. Okay? So instead of C times V plus minus V minus, we also have to include the threshold voltage term in there. That determines the amount of charge in the channel. And as I said, we have less charge on the right side than we do on the left side. It's a function of x, a linear function of x. So you start with the differential form. Okay, ID is equal to mu times Q times V. So this is a basic equation for current versus voltage. Then we split it up into smaller pieces. Okay, this is the thing where we're splitting up the larger resistor into smaller resistors. Okay, and each one of these resistors has a width, dx, if we go back to this equation, the current times dx is equal to this value here. So we took this equation on the top and we differentiated it to get a differential form of it. Okay, so this is the current multiplied by the size of that resistor, the length of the resistor, and this is equal to mu n times the width is the other dimension of the transistor. This is how wide the transistor is when you look at it from the top view. Okay. And then Qn of x, this is the amount of charge that we have as a function of x, and then we have this dVx on the right side. This is the difference in voltage between one side of this resistor and the other. So we took this basic equation and put it into a differential form. Now we take that differential form and we integrate it. As I mentioned earlier, we have to do integration in order to find the relationship between current and voltage. So we have a resistor that's sort of a nonlinear resistor. The resistance varies depending on the position in the channel. To find the total resistance, we integrate both sides of this equation. So this is a little mathematical trick. If you have, let's say we have two different variables. Okay, this one, the left side of the equation is in terms of x, so it's dx. The right side of the equation is in terms of voltage, dV. So you may or may not remember this, but if you integrate both sides of the equation, you can integrate both sides of the equation with respect to different parameters, and that's still mathematically valid. So you just have to make sure that the parameters the limits of integration, they match up. So we are integrating, conceptually, we are integrating from the left side of the channel to the right side of the channel. So we are integrating from x equals 0 to x equals L, if we're considering the variable x. So this is x equals 0, this is x equals L. So we're integrating from the left side of the channel to the right side of the channel with respect to x. So this is the left side of the equation. The right side of the equation, we have to also integrate from the left side of the channel to the right side of the channel. But this is in terms of the variable V. V is equal to 0 at the source because the source is connected to 0 volts, and the voltage is equal to VDS, it's equal to the drain voltage on the right side of the channel. So that's why the limits of integration are V equals 0 and V equals VDS on the top here. So we integrate both sides of the equation just in terms of different variables. This side of the equation becomes IDL, and this side of the equation, just do a little bit of math here. We're integrating with respect to V. You have a linear function here. The integration of a linear function is a quadratic function. So this is all like basic integration here at this point. And this gives you the equation for the current in the triode region. So let's look at the results of this equation. There's two terms in it. There's a linear term, and there's a linear term, and then there's an exponential term. All right, this equation describes the triode, the current in the triode region, just here like this. Okay. That equation describes the current in this triode region. Now, just conceptually speaking, it looks like an inverse parabola. Right? This part starts to look like an upside down parabola, and this part here looks like a linear function, a line. So where does that come from in the formula? This term here is a linear term. When you're at very small values of the drain voltage, okay, this linear term becomes more significant than this one. Remember, quadratic functions, they decrease very rapidly as you go to 0. Linear functions, they also decrease, but they decrease at a slower rate. So when you're at small values of VD, this term will become insignificant compared to this term. Okay, at small values of VD, now you have a linear relationship between ID and VD. So this is why it's called the linear region. If you ignore this term, there's a linear relationship between ID and VD. Okay, and the channel resistance, you can figure out according to this formula. Remember, like if you have a line, the slope of that line tells you the resistance, right? A resistor gives you a linear IV characteristic, and the slope of that line tells you the resistance. So what you're doing here is you're just finding the resistance by looking at the slope of that line. Okay, and mathematically they're doing it by taking the derivative of voltage divided by the dV di. That gives you 1 over R. If you take di dV, that will give you the resistance. So this is a way to find the equivalent resistance in the triode region. So in other words, this thing is behaving as a resistor from source to drain, and we've just found the value of that resistance. So when we go to the saturation region, now we're talking about this portion of the curve. In the saturation region, the current it saturates, it limits at a specific value. Saturation occurs when the drain to source voltage is greater than or equal to VGS minus VT. This is when the channel starts to pinch off. Again, we will derive the threshold voltage in a little bit later. The onset of saturation occurs at VDS is equal to VGS minus VT. This is defined as VD sat. And if we plug in VD sat in the equation that we derived earlier, we get an equation for the current in the saturation region. Okay, if you ignore channel length modulation, that's something we'll talk about later. It's a second order effect, but some of you know about it already. If you ignore channel length modulation, the current in the saturation region is not a function of VD. You can see it's just a function of the gate voltage. So that's why in that transistor curve you get a flat horizontal line. And you can calculate what that current is. It's dependent on the gate voltage and threshold voltage, and then some of the physical parameters. So we have a few minutes here, so we'll just we'll probably end off with this. Comparing the PMOS and the NMOS device. The PMOS device works the same way as the NMOS device, except the polarity of the current, gate voltage, and drain voltage is reversed. So the current voltage characteristics for an enhancement mode NMOS look something like this. This is what the structure of an NMOS device looks like. This is the one we've been looking at over the last few slides. The source and the drain regions are both N+. The substrate is P-type. And when the device is on, you form an N-type channel between the source and the drain. To form that channel region, you have to apply a positive gate voltage. And this is what the IV characteristic looks like for an enhancement mode NMOS device. For a PMOS device, it's the opposite. And I do want you to look at this closer, even though we're kind of doing it rather quickly in class. In the final exam, I always ask questions about PMOS devices because it really tests your understanding of the basic concepts of how the transistor works. So in a PMOS device, it's the same idea, except everything's in reverse. You have an N-type substrate instead of a P-type substrate. The source and the drain are both P+, and you form a P-type channel underneath the gate. Now keep in mind, and this is the thing I want you to understand very well, the gate, in order to turn on a PMOS device, you actually have to apply a negative gate voltage. Okay, and go through and understand the physics of the PMOS device on your own. The electric field is pointed up instead of down. You attract holes, you attract minority holes to the channel region rather than minority electrons. It's exactly the inverse of the NMOS device, but do understand the physics of that. Okay, in a PMOS device, you apply a negative voltage to the gate, and you also apply a negative voltage to the drain as well. So your currents end up being negative like this. You can go through and understand that on your own. This is an enhancement mode PMOS device. There are also depletion mode devices. The depletion mode devices are ones that are normally on. In other words, they have a conductive channel even at 0 gate voltage. So if we were to compare an enhancement mode NMOS device versus a depletion mode NMOS device, you've learned in your previous classes that in an enhancement mode, a typical transistor would have a positive threshold voltage. Let's say like 0.5 volts or 1 volt is a typical threshold voltage for an NMOS transistor. A depletion mode device would actually have a negative threshold voltage. So that means if you have an NMOS device with a negative threshold voltage, this means that the device is on even when no gate voltage is applied. All right. So you might be wondering, like, well, that doesn't really make any sense. Like if you have, going back to this graph here, how can you possibly have an inversion channel if you don't apply any voltage to the gate? Well, the reason for this is more complex. But I will say that the way that it works is that you do something called ion implantation. Okay, the ion implantation can actually create some negative charges in there, so that you actually have a conductive channel even at zero bias. The answer is actually a little bit more complicated than that, because it'll make more sense when we start talking about threshold voltage calculations. The threshold voltage depends on a lot of factors. It depends on the metal to semiconductor work function. It also depends on the substrate doping levels. It also depends on the depletion charge. So by tuning some of those parameters, you can actually get negative threshold voltages. Okay, but there is a step called ion implantation, which actually implants a certain amount of charge in the channel region. So it is possible to have negative threshold voltages. In an enhancement mode NMOS device will have a positive threshold voltage. In depletion mode NMOS device will have a negative threshold voltage. With NMOS devices, you always apply a positive gate voltage, and you apply the current flows from drain to source for NMOS devices. For PMOS devices, the threshold voltage is negative for an enhancement mode device. The threshold voltage is positive for a depletion mode PMOS device. And in both cases, you apply a positive source to gate voltage, and the voltage flows from source to drain, or the current flows from source to drain rather than from the drain to the source. So keep these, make sure you keep these different 4 types of devices, be able to differentiate between them. So this is something that sometimes I do in class and sometimes I do out of class. So for this semester, I would like you to just do this problem on your own. Okay, you have it in the notes. The notes are on Blackboard. Our quiz will be on this question. Okay. Assume you have an N-channel MOSFET with some given electron mobility, a given gate oxide thickness. A VT is equal to 0.6 volts, and the dimensions here. I want you to calculate the drain current when VG is equal to 5 volts, VD is equal to 0.1 volts, and tell me what region of operation are you in. And then the same thing when VG is equal to 3 volts and VD is equal to 5 volts. These are relatively simple, straightforward calculations, but there's just a few little things with the units and figuring out, this gives you mu n, for example. The oxide capacitance, you have to figure out the oxide capacitance by using the gate. You have to use epsilon of the oxide, the dielectric constant of the oxide, divided by the gate oxide thickness. So there's just a little bit of details for you to look at. So make sure that you do this problem on your own. We'll have a quiz on it next week. They're relatively easy problems, okay? So at this point, you'll be able to do the basic calculations of calculating the currents in the saturation region and the triode region. Next week, on Monday's class, these are the answers, by the way. You can check your answers over. Triode region should be 0.75 milliamps. Saturation could be 4.8. Next time in class, we're going to start talking about the more complex aspects of the energy band diagrams and calculating the threshold voltages. Yes? Tuesday. Yes. Have a good weekend.